So this is the review sheet for 1-1 to 1-3. So starting on 1-1, we're going to rewrite each expression using the property they give you. So we're given 15 minus 3 as the expression, and we're going to rewrite that using the algebraic definition of subtraction, which says subtracting a positive is like adding a negative. So 15 minus 3 is the same as 15 plus negative 3. So we've rewritten it. It still has the same value. Okay, but based on the algebraic definition of subtraction, subtracting a positive or subtracting any number with that in mind is the same as adding the opposite of that number. So number 2, the algebraic definition of division says dividing by 1/2 is the same as multiplying by the reciprocal. If you flip this 2 over 1 to 1 over 2, okay, and you multiply by it, you get the same answer. So let's test it first of all. 1/2 is the same as 0.5, right? So 0.5 divided by 2 is 0.1. Oops. I was like, that doesn't make sense. 0.5 divided by 2 is 0.25, right? 50 cents divided by 2 is 25 cents. So we want to double check. The algebraic definition of division says I can multiply by the reciprocal. So instead of dividing by 2, I can multiply by the flipped version, or 1/2. You may have learned this is KFC, keep, flip, change. Instead of dividing, you flip a fraction, you multiply. So let's see, 0.5 times 0.5. Sure enough, I get 0.25. So this holds true. Associative property says that we can rearrange the grouping symbols or parentheses and still get the same answer. So right now the 5 times 3 is grouped, and then we multiply by 1/3. So what happens if we change the grouping and put the parentheses around 3 times 1/3 and leave the 5 out here? Well, if you run these numbers, you get the same answer, even though you did this first. Multiplication is associative, so that just means that you can rearrange the grouping, do it in a different order, and still get the same answer. Same thing holds true for addition. So I'm going to go ahead and rearrange the grouping and put the parentheses around the 2 plus 8, which just means if I was going to complete this and evaluate it, simplify it, okay, I would do this first. So 7 plus 2 is 9, plus 8 is 17. Well, what if I do this first? 2 plus 8 is 10, plus 7 is 17. All right, number 5. First of all, it says state the first operation. That's just talking about plus, minus, times, divide. Those are your operations. So based on the order of operations, or PEMDAS, what's the first thing you're going to do? So the first thing you're going to do is parentheses, but you're not going to write parentheses because they're asking for the actual operation. So addition is the first operation you're going to do. Now normally it's not, right? You do your parentheses, exponents, you multiply and divide, and then you add and subtract. But in this specific problem, we're going to do addition first because it's in parentheses. So the first operation you perform is addition. Now, this says the square root of, and I've gotten a lot of questions on that. I'm not sure how much exposure there was on that for you in middle school. But square root of something, if you have 5 squared, you get 25. The square root of 25 is like going the opposite direction. What number squared gives me 25? What number times itself gives me 25? So it's 5. The square root of 25 is 5. So it's going backwards from squared. So in this case, first thing we're going to do is add, and you get 9. So we're taking the square root of 9, which means something squared equals 9. What number times itself gives you 9? 3 squared is 9. So the square root of 9 is 3. You can find that on your calculator right above the squared button, which makes sense because it's the opposite here. So what you got to do is hit second and then this squared button to bring it up. 9, you don't even have to close the parentheses. You can, but you don't have to. You can just hit equals and it'll give you the answer. So that's 3. This whole thing is 3. And then don't forget to also divide that by 3 now. So 3 divided by 3 is 1. Okay, number 6. What's the first thing you should do? Well, we're going to do whatever's inside parentheses, and that's subtract. So in this problem, you're going to subtract first. And now let's go ahead and run the numbers. You're going to subtract. These are also grouped because they're on the top and bottom of a fraction. So those have to happen first. So you're going to get 18 on top, you're going to get 9 on the bottom, plus 5, and 4 minus 2 is 2, so raised to the second. Now, 18 divided by 9 is 2. 5 squared is 25. Put them together, your answer is 27. Okay, number 7, evaluate, which basically just means solve the algebraic expression for the given value of the variable. So it's just a fancy way of saying solve this for this. So when x equals -2, what is this value? So you're going to rewrite this, but with -2 plugged in for x. So the problem is 3x to the third. We're going to rewrite it with -2 in there for x. So 3 -2 raised to the third. Now notice I put it in parentheses. That just helps to group the negative with the 2. So it's not just the 2 being raised to the power, it's the negative. It's very important when you punch these in your calculator. I'm going to hit on that a lot as we go forward. We're going to put -2 in parentheses, and then we're going to raise it to the third power. And you get -8, then times by the 3, and you get -24. Now, one trap I saw people already falling into today was they wanted to multiply here and do 3 times -2, take that answer and raise that to the third power. Okay, problem is, going back to PEMDAS, exponents before you multiply and divide. So you can't multiply and then do an exponent. Exponents first. Okay, number 8, rewrite this, c equals 2, d equals 3. So instead of c plus 1, it's 2 plus 1 over 2. And instead of raised to the d, it's raised to the third. So let's complete the top here first. This is 3 over 2 raised to the third. So that's the same as writing this 3 times. 3 over 2 times 3 over 2 times 3 over 2. You can multiply straight across. 3 times 3 times 3. That's 27. 2 times 2 times 2. That's 8. You also could have stopped right here, and if you use your fraction button, so 3 over 2 in parentheses, raised to the third power, it gives you it like this. Now that's equivalent. If you remember how to simplify an improper fraction, 8 goes into 27 3 times with 3 left over. So that's not going to give you the nice answer that you want, but you could do them individually. 3 raised to the third is 27, and then 2 raised to the third is 8, and then there's your answer right there. Okay, number 9, rewrite this using addition instead of subtraction. So again, this is the algebraic definition of subtraction, going back to that. So instead of writing it as a minus, you can write it as a plus, but then this becomes the opposite. So 12 plus, instead of -20, positive 20. That gives you the same answer. But we need to understand why we're doing this. 12 minus -20 is 32. That's the same as 12 plus 20. That's the algebraic definition of subtraction that says that. Subtracting something is the same as adding its opposite. Okay, here we're going to rewrite this. The multiplication part isn't actually involved. We're just changing subtraction to addition. So instead of 1 minus +9, it's 1 plus -9. And that's it. It doesn't ask you to evaluate, so we don't have to solve this. It's done. 11, rewrite the expression using multiplication instead of division. So instead of divided by 21, it's the same as times 1 over 21. That's the algebraic definition of division. Instead of divided by 4, it's the same as times by 1/4. 13, if all of this is true, what conclusion can be made based on the transitive property? So transitive property is when two different things are equal to the same thing. That means they're equal to each other. So what I notice is d plus 9 shows up in both of these equations. So in the first one, a minus 32 is equal to it. In the second one, p squared is equal to it. Well, if each one of those is individually equal to d plus 9, that means they're also equal to each other. So the conclusion is that a minus 32 is equal to p squared. Okay, flip it over. We're just going to use the order of operations to evaluate this. So we want to evaluate this when x equals positive 2. So you're going to rewrite it and plug 2 in for x. So 2 minus 6 is -4. So now we're going to plug 6 in. So it's 6 minus 10 times -4. Order of operations says parentheses first. So in here, 6 minus 10 is -4. Times that by -4, you get 16. Plug 4 in here. 4 minus -8. Minusing a negative is like adding a positive. This is 12. Plug x in, 12 minus 5 squared. So that is parentheses first before exponent. So parentheses first gives you 7. The squared is still there. 7 times 7 is 49. X equals 18. This says 3 divided by 18. We try that in our calculator, 3 divided by 18, and you're going to get a nasty decimal. Please don't give me this answer. That's not a good answer. So when you get division and it doesn't give you a nice number, rewrite it as a fraction, 3 over 18. This says 3 divided by 18. We need to know that a fraction says divide by. And we don't leave fractions unsimplified. So this is the correct answer. 3 over 18 is the correct answer. But it should be simplified, which means divide them both by the same number, which would be 3. And then your final answer is 1/6. Let me show you how those are equivalent. 3 divided by 18, or 3/18, gives me this. So 1 divided by 6 should give me the same answer. And it does, because they're equivalent. All right, number 19, plug in 2. So we're going to end up with 12 divided by 4. So that's 3. Plug in 15. 15 plus 3 first in parentheses. So that's 18. And then divide by 6. So that's 3. 21. Dividing by 10. So it's 5 squared divided by 10. 5 squared is 25. 25 divided by 10. That's a nice decimal. That's acceptable. If you put 2.5 as your answer, it's good. Now, that's not what the key says. So you leave it as 25 over 10, the fraction. That can be simplified, so you divide them both by 5, and you end up with 5 over 2. These are the same. 5 over 2, 5 divided by 2 is 2.5. Okay, so these are equivalent. Either answer is fine. So basically, moral of the story is if you get a decimal that ends, you can use it, like 2.5. If you get a decimal that goes on forever, we're not using those. Okay, those are not useful. All right, number 22, using grouping symbols, write how you would input this into your calculator. So if I could, I'd probably just omit this question. Okay, but when we try and write something, so let's go with something with numbers like 3 plus 2 over 4 minus 1, something like that. If I was going to try and put that into my calculator, I cannot just put it in this order, because if I do, if it looked like this, 3 plus 2 divided by 4 minus 1, if I just write it all in like that, your calculator knows the order of operations. It's going to look at this whole sentence and say, I have to divide before I add. But we know that when you have one of these fractions, these are actually in parentheses, and you have to do the whole top first, and then the whole bottom, and the last thing you do is divide. So we have to tell the calculator that. And so you have to actually type it in like this, in parentheses, 3 plus 2 divided by, in parentheses, 4 minus 1. So it has to be grouped like that if you want it to follow that order. And so for this one, we just have to show that we would group the top. So when it says grouping symbols, that's parentheses. So you put 3p minus q in parentheses. This means divide, so you would hit the divide button in your calculator, and then in parentheses, 2p. So anytime you have one of these fractions and there's operations to complete, if you were going to put them in the calculator, you have to put parentheses so it doesn't do the division until the end. Parentheses say do this first, then divide. Okay, 23. Let's go ahead and evaluate this now with these numbers plugged in. So the top becomes 3 times p, which is 8, minus q, which is 5. We need to know that you can write it like this. If you write it as 3 times 8, that's fine. Okay, but we need to know that parentheses means multiplication. And the bottom is 2 times p, so 2 times 18. So first of all, 3 times 18 is 24. And you're going to minus 5, so you're going to get 19 on top. The bottom, 2 times 18 is, oh, not 18, 2 times 8 is 16. So we get 19 over 16. 19 divided by 16. Now you notice that's like a longer decimal, right? But it doesn't fill up my whole screen, which means they didn't round this. This is the whole answer. Okay, it stops at the 5. There's not more numbers that come after it. And so this is a perfectly acceptable answer. But I want you to know, so is this. Either one of these is fine. You can leave it in fraction form or put it in the decimal form. If this was a decimal that filled up your whole screen and went on forever and you had to round it to put it on your paper, then I actually want you to leave it as a fraction. 24. Which expression is not equal? Negative 15 plus 5 is negative 10. 5 minus 15 is negative 10. 5 plus negative 15 is negative 10. 15 more positives plus just 5 negatives means I'm left over with 10 positive. So that's the one that is different. Okay, looking at these, when I first look at this one, I see division. I'm going to kind of ignore that for a second. This one's already simplified, right? So I'm just looking for something that matches this. When I see multiplication, I know it's nice and easy. You can multiply straight across. It's negative 3 over 7. So those two are equal, meaning one of these is going to be not equal. What you want to do is you want to turn both of these to multiplication using that property we talked about earlier. So it's negative 1/3 times, and then you flip this one to 1 over 7. Same thing here. This is 3 over 1. Flip it to times, flip this to negative 1/7. Multiply straight across, and you're going to get negative 3/7 here, and here you're going to get negative 1 over 21. So that's the one that's different, letter A. 26, scanning it quickly, we're talking about transitive property here. So again, two things are equal, that means, two things are equal to the same thing, which means they're equal to each other. So if Lincoln has the same number of baseball hats as Rick, and Rick has the same number of baseball cards as Maggie, so Lincoln has the same as Rick, Maggie has the same as Rick. What conclusion can we make? Lincoln equals Maggie. If both of them are the same as Rick, then that means they are the same as each other. Okay, 1-2b. Let's practice using our calculator here. You can do this by hand, but I'm not expecting you to. 4 times, put it in parentheses, 7 over 2. So you hit 7, ABC button, 2. If you don't have one of these calculators yet, you need to get one. It'll make your life much easier. Plus 1, it's 15. 8 times, in parentheses, 5 over 2. Plus 1 is 21. 2 times, in parentheses, 3 over 2. Plus 1 is 4. Okay, you can actually put all of it in there at once. Now, they want you to notice that this is a pattern. So take a look. You are putting different numbers in for this front number and the top number. I don't see a correlation between the two, so it can be any numbers you want, but the 2 better be there and the 1 better be there. So you're going to put some number up front. I'm going to put 5. I'm going to put some number up top. I'm going to put 10. But you better have a 2 here, and you better have a plus 1 here. Okay, that's another instance in the pattern. All right, number 5. 5 and 6 give 2 instances of each pattern. Instances are just examples, okay, with numbers plugged in. X is the only variable here, so you got to put the same number in every single time. So I'm going to do it with, let's do it with a 10. 10 squared minus 1 equals 3 times 10 minus 1. Do it again with 100. 3 times 100 squared minus 1 equals 3 times 100 times 100 minus 1. Same thing here. It's x's. Okay, so it's negative 5 times. Put any number we want in here. I'm going to put 3. Plus 6 equals negative 5 times x again. Same number that you plugged in. 3 minus 30. And do it one more time, but pick a different number than 3, so 2. Negative 5 times 2. All right, number 7 is the opposite direction. They're giving you 3 instances. You describe the pattern using a variable, so an x or whatever letter you want. But notice the 7 is the same every time, so that needs to be in our pattern. This number has changed. That's your variable, so times x. This number is the same every single time, so be careful. That's not an x. Even though it matches this 2, it doesn't match the 3, it doesn't match the negative 1. So if I'm plugging in negative 1 for a variable, it should be here if that's a variable, and it's not. So that minus 2 has to stay times, now this is the number that matches the input. So that is a variable, x. Divided by 5 happens every time. Equals, 5, 5, 5. Happens every time. Now here's the 2 again, and the 3 again, and the -1. There's your variable. And then divided by 5 happens every time. Okay, evaluate just means get the answer. So follow your order of operations. Parentheses first. So it's going to be 3 times 3 to the third. Exponents next. So we're going to do, before you multiply here, you got to do 3 to the third. So 3 raised to the third is 27. Then times that by 3, it's 81. Parentheses first, 3 times 4 to the third. You got to do 4 to the third first. So 4 raised to the third, 64. Times 3 at the end is 192. Parentheses first, 3 minus 1 is 2 to the third. 2 to the third, plug in your calculator, that's 8, and 8 times 3 is 24. Write another instance. So if you look, the 3 is the same every time, raised to the third is every single time. Okay, so we're just going to write this over. It's -1 every time. So it's 3, plug in a different number than 4 or 5 or 3. So I'm going to put 10 minus 1 to the third. So the 3 stays, the -1 stays, the exponent stays. The only number that's being changed, that's your variable. If you were going to write this with a variable, it's in that position. So coming up with another instance, plugging a different number in. All right, 3 instances are given. Describe the pattern. So again, if you see the same number, it stays. Once you see this number being replaced, so notice it's here and it's here. The 4s match, the 5s match. That's your variable. The 7s are the same, the 4s are the same, the 2s are the same, the 10s are the same. So that's my only variable. X plus 7, the -4 stays, equals, the 2 is here, times the variable, plus 10. Okay, here, the 3s are the same. Here's a 2, a 1, a 3. So where else does that 2 show up? Here and here. Where does the 1 show up? Here and here. Be careful, this 1 is different. And where does the 3 show up? Here and here. This 3 is different. Because that 3 shows up every time, that is not the variable. These are changing every single time. Those are the variables. So 3 times x squared plus, this is all the same, so it stays. This is all the same, so it stays. This is the variable, times x plus 1. Any letter you want. You see on the answer key they use n, doesn't matter. And here, 5s are the same, so that stays. 2s are the same, that stays. 2, 3, 4, so there's our change. There's our variable, so where else is the 2 where it's changing every time? Right here, 2, 3, 4. These 2s stay the same, so that is part of it. That is not the variable. So we have x plus 5 equals 2 times x plus 7 times 5. The rest of it is constant. All right, and last of the required pages. You do not have to do 1-3b. If you want more practice, you can though. All right, we're going to consider 3 instances of the pattern. Describe the pattern using 1 variable. So whatever's on the inside of absolute value, you get the positive version. That's what's happening here. So if I was going to describe this with a variable, absolute value of x equals x. Different numbers are being plugged in for x, right? Find another example of this. So the square root of 3 is 3. Not square root, I'm sorry. Absolute value of 3 is 3. Find a counterexample. So absolute value from our lesson makes things positive. So the absolute value of -5 is positive 5. So that would be a counterexample right there. Absolute value makes it positive. What it's actually asking you is how far is this number from 0? So when you ask yourself how far is 3 from 0, it's 3 away. So the answer you plug in here is the answer you get here. But when you ask yourself how far away is -5 from 0, it's 5 away. Absolute value is always expressed as a positive because it's a distance. The distance from 0, whether it's up to +5 or it's back to -5, when you're measuring that distance, it's 5. When you're measuring that distance, it's 5. It doesn't matter which direction you go. That's what absolute value is. So this would be a counterexample because we did not get -5. We didn't get the number we plugged in on this side. All of these patterns here, whatever number we plugged inside the absolute value, it gave us back as our output or our answer. In this case, we plugged in a negative number, we got a positive, not what this pattern was showing. So this is called a counterexample. Number 4, using the table, evaluate each expression for 4 different values. So this n means these are the values you're plugging in. So I'm going to go 0, 1, 2, 3, just easy numbers. We're going to go ahead and run them in here. So if I plugged in 0, I'm going to get 0 here, I'm going to get 0 here, I'm going to get 0 here, so my answer is just 5. If I plug in 0 here, I get 12. So right away, I know these are not equivalent. They're going to ask me that question later. So I plug 1 into all the spots and run it. I plug 1 into this spot and run it. So when I do that here, I get 17. When I plug 2 in here, I get 39, 71. You're just plugging in and evaluating. So we're not going to actually write those out, but you would have to plug those in the calculator, go all the way through. And you could have chosen different numbers. You didn't have to use 0, 1, 2, 3. So your numbers here might be different than mine if you chose a different number. The key is that we see that these do not match. Now they matched up here, but nowhere else. So use your results to determine whether these expressions are equivalent. If they're equivalent, every single answer here has to match every single answer here, and they don't. So my answer is not equivalent. And if I want to get fancy with my language, my explanation, because it does ask you to explain, is not every input produces the same output. Basically, you could say every answer is not the same, but this is the fancy way to say it. All right, last question. We're going to draw the 4th instance of the pattern. So there's going to be how many circles? 1, 2, 3, 4. 4th instance. And so we're going to have a triangle here, and we're going to have a triangle here, and each one of these is going to have a triangle on top. How many circles and how many triangles will there be in the 10th instance? Now you could count this out, right? You could start to figure it out. So let's say you made a chart. Now circles is easy, right? First instance, 1. Second instance, 2. Third instance, 3. So there are going to be 10 circles in the 10th instance. But what about these? We've got 4. 1, 2, 3, 4, 5, 6, 8. So you're counting by 2s up. So you could go all the way out to term 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, if you wanted to do it this way. So 1 has 4, and then it goes 6, 8, 10, 12, 14, 16, 18, 20, 22. And so the answer here is 22 triangles. That's the long way to do it. Now we're going to talk about how do we do it using an expression. So let's say this instance was the 200th instance. Well, I don't want to make a chart and go all the way out to 200. No way. I'd rather make the expression that does the job for me. So first of all, how many circles are needed to make the nth design? When you see nth, it just means any term. If I ask you any term, how many circles are there? So 3 is the n. And how many circles are there? 3. 4 is the n. How many circles are there? 4. So whatever n is, that's how many circles there are. So how many circles are needed to make the nth design? N circles. Now, triangles, not so easy. Okay, term 1 has 4, term 2 has 6. We talked about you can count up like this, but let's come up with a pattern. We talked about what's the rate of change. The rate of change, this is going up by 2 every single time. They're adding 2 every single time. So when you start writing this, it's going to be 2n. You start there. Then you got to figure out, is there a plus or a minus on this expression to get me to the right thing? So you start double checking this. If I plug in the terms, which is the 1, the 2, the 3, is this expression actually giving me how many triangles there are? So if I plug in the 1, 2 times 1 is 2, but it was supposed to be 4. If I plug in term 2, 2 times 2 is 4, but how many triangles is it supposed to have? 6. If I plug in 3, 3 times 2 is 6, but it's supposed to be 8. So every single time it is off by 2. So all I have to do is take this expression and convert it to get it to where I need it to. I need a plus 2. Now when I plug in any of these numbers, like let's say 4, plug in 4, 2 times 4 is 8, plus 2 is 10. There are 10 triangles. So if I asked you the 200th term, all you got to do is plug in 200 times 2 plus 2, and you know how many triangles there are. For the sake of doing one more of these, I'm not going to do this whole back page because it's not required for your homework tonight, but I do want to take a look down here. So it says draw the fourth instance. I'm not super concerned with that. You could figure that out. How many circles and how many line segments would there be? That's basically you counting out that way. But I want to focus on the nth. So I just want to look here at number 8. So let's make a quick chart. The circles are just n because this is term 1, term 2, term 3. So there's 1 circle, 2 circles, 3 circles. But the line segments, they don't follow that. So we're doing lines and we're doing terms. And actually, I prefer you to do it the other way. So terms on top, lines down here. So term 1, term 2, term 3. That's all we have right now. How many lines are in term 1? There's 2. How many lines are in term 2? There's 3. How many lines are in term 3? 4. So what's the rate of increase? It's going up by just 1 every single time. So that would be a 1n. Now, in algebra, we don't normally write a coefficient of 1. 2n, sure, but 1n we normally don't. So you're not going to see the 1 on your answer key. You're just going to see an n, but we need to know that they say the same thing. Now, if I actually take this now and plug that in, technically I'm timesing by 1. 1 times 1 is 1, but I need it to be 2. Plug it in, 2. 2 times 1 is 2, but I need it to be 3. Plug in 3. 3 times 1 is 3. I need it to be 4. So every single time I'm just getting the term, and I need to add 1 to get it up. So this should be a plus 1. And you'll notice that the answer key provides it like this because, again, we don't need to write a coefficient of 1.